In the infinite theater of the cosmos, where time and space are intertwined, a presence lurks and defies understanding. Invisible yet incredibly powerful, these entities hold the key to some of the universe's greatest secrets. They are dark, massive, and mysterious. Three telltale signs of the mysterious world of black holes. Space is often idealized for its beauty, but its dangers are equally profound. The concept of black holes has always fascinated and terrified scientists and astronomers alike. A recent revelation by deGrasse Tyson has brought these celestial behemoths back into the spotlight. Prepare to explore the mysteries of black holes, their origins, and their potential to reshape our understanding of the universe. Join us on this intergalactic journey to explore one of the deepest questions in science. What are black holes? Black holes are some of the most mysterious and fascinating objects in the universe. Their very existence challenges our understanding of the universe, because they are regions of space where gravity is so strong that not even light can escape. The concept of black holes was first proposed in the early 20th century, but it was only later that scientists began to collect observational evidence that they existed. The black hole forms when a massive star runs out of nuclear fuel and collapses under its own gravity. This collapse results in a singularity, a point of infinite density, surrounded by an event horizon, the limit beyond which nothing can return. The gravitational pull near a black hole is so strong that it distorts space-time, creating some of the most extreme conditions in the universe. The formation of black holes is a story of cosmic violence and transformation. Stars, the true nuclear furnaces of the universe, spend most of their lives converting hydrogen into helium through nuclear fusion. This process generates the energy that allows the star to shine and provides the outward pressure needed to counteract the gravitational pull of the star's mass inward. However, when a large star, typically more than 20 times the mass of the Sun, runs out of nuclear fuel, it can no longer maintain this delicate balance. The core collapses under the force of gravity, resulting in a catastrophic supernova explosion. The outer layers of the star are ejected into space, while the core continues to collapse. If the remaining mass of the core is large enough, usually about 3 times the mass of the Sun, it will compress into a singularity, forming a black hole. There are several types of black holes, each with its own characteristics and formation mechanisms. The 3 main types of black holes are stellar black holes, intermediate mass black holes, and supermassive black holes. These black holes form from the remains of massive stars that have undergone supernova explosions. They typically have masses between 5 and 20 times the mass of the Sun. Despite their relatively small size, their density is very high, resulting in a gravitational field strong enough to trap light. Intermediate mass black holes have masses ranging from a few hundred to a few thousand times the mass of the Sun. How they form is less well understood, but they may form through the merger of smaller black holes or the collapse of large star clusters. These black holes are thought to occupy the centers of some star clusters and small galaxies. Found at the centers of most galaxies, including our own Milky Way, supermassive black holes have masses ranging from millions to billions of times the mass of the Sun. Their origin remains the subject of intense research, but they are thought to form through processes involving the accumulation of large amounts of gas and dust, as well as the merger of smaller black holes. Supermassive black holes have a profound effect on their host galaxies, influencing star formation and galaxy evolution. Central to the concept of a black hole is the event horizon, the limit beyond which nothing can escape the black hole and its gravity. The radius of the event horizon is proportional to the mass of the black hole and is known as the Schwarzschild radius. For a stellar black hole, this radius is typically only a few kilometers, while for a supermassive black hole it can extend for millions of kilometers. Inside the event horizon is a singularity, a point where the density and gravitational force are infinite. According to general relativity, the laws of physics as we know them no longer apply to singularities. This poses a fundamental challenge for scientists, because our current understanding of physics cannot completely describe what happens inside a singularity. To address this problem, researchers are exploring theories that attempt to unify general relativity and quantum mechanics. One of the most promising approaches to understanding the nature of singularities and the behavior of black holes is the theory of quantum gravity. Quantum gravity seeks to unite the principles of quantum mechanics, which govern the behavior of particles at the smallest scales, with general relativity, which describes the behavior of gravity at large scales. Biggest point: one of the leading candidates for a theory of quantum gravity is loop quantum gravity. This theory holds that spacetime itself is quantized and made up of discrete, indivisible units called spins or lattices. In this framework, spacetime is not a continuous fabric but a collection of interconnected loops. This quantization of spacetime prevents the formation of infinite density singularities, leading instead to quantum bounce and rebound, where the collapsing matter bounces back, forming a new region of spacetime. The study of black holes has advanced significantly in recent years thanks to revolutionary observational techniques and technological advances. In April 2019, the Event Horizon Telescope (EHT) collaboration captured the first image of a black hole. The supermassive black hole is located at the center of the M87 galaxy, about 55 million light-years from Earth. The image shows a ring of bright, hot gas surrounding the dark center, providing visual evidence of the black hole in its event horizon. Gravitational wave observatories, such as LIGO and Virgo, have also contributed to our understanding of black holes. These observatories detect ripples in spacetime caused by the collision and merger of black holes. The first detection of gravitational waves in 2015 marked a monumental breakthrough, confirming the existence of a binary black hole system and providing indirect evidence of the existence of black holes through gravitational wave signals. The powerful leads they create point: one of the most intriguing theoretical predictions about black holes is the phenomenon of Hawking radiation, proposed by physicist Stephen Hawking in 1974. According to this theory, black holes are not completely black but emit radiation due to quantum effects near the event horizon. Particle-antiparticle pairs form spontaneously near the event horizon, with one particle falling into the black hole and the other escaping. This process results in a gradual loss of mass from the black hole, leading to its eventual evaporation over extremely long periods of time. Hawking's concept of radiation also raises important questions about the fate of information falling into a black hole. According to classical general relativity, information about matter entering a black hole is lost forever at the singularity. However, this idea conflicts with the principles of quantum mechanics, which hold that information must be conserved. This discrepancy is known as the information paradox. To resolve the information paradox, several theoretical advances have been proposed. The holographic principle suggests that information contained in a black hole may be encoded on its event horizon, challenging our conventional understanding of space and information. Another proposal, the firewall paradox, suggests that the event horizon of a black hole may be surrounded by a firewall of high-energy particles, potentially resolving the problem of energy information loss but raising new questions about the nature of space. Time near a black hole. Black holes are not just isolated phenomena. They play a major role in the evolution of galaxies. Supermassive black holes, which lie at the centers of most galaxies, exert profound effects on their host galaxies through processes such as accretion and feedback. As matter falls into a black hole, it forms an accretion disk, releasing enormous amounts of energy. This energy can create powerful streams and jets that impact surrounding gas and dust, driving star formation and galaxy evolution. The interaction between supermassive black holes and their host galaxies is a dynamic and complex process. Observations have shown that the mass of a supermassive black hole correlates with the mass of the galaxy and its bulge, suggesting coevolution of black holes and galaxies. Understanding this relationship is crucial to understanding the history and future of galaxies, including our own Milky Way. Besides the well-known types of black holes, there are also theoretical variations with unique properties. For example, charged black holes have an electric charge in addition to their gravity. There are two main types of charged black holes: Reissner-Nordstrom black holes, which are charged but do not rotate, and Kerr-Newman black holes, which are both charged and rotating. The presence of electric charge causes additional forces and phenomena, such as frame drive, in which a spinning black hole twists surrounding spacetime. Another exotic variation is the primordial black hole, which is believed to have formed in the early universe. Unlike black holes that form from the collapse of massive stars, primordial black holes may form from density fluctuations in the early universe.